In this video, we're going to go over how to convert from different bases to others. So for instance, from base 2 to base 10 and so on. So we'll begin just by recalling the idea of expanded notation, which we learned in our previous lesson. This will be essential whenever we talk about representing numbers in different bases. All the numbers that we are used to experiencing most likely have been in base 10 in our lives to this point. So for instance, 53,417 could be written in expanded notation like this. And the nice thing about expanded notation is it helps us see the base 10 system at work. For instance, we've got 7 ones represented by 10 to the 0. And then the next term is 1 times 10 to the 1, which is 10. So that's what represents this 10 here in the positional number system. And then what happens is we keep increasing the powers of 10 as we go to the left of the number. So for instance, next we see 10 squared, and then next we see 10 cubed representing 1,000. And then finally, for this number, 53,417, the largest power of 10 is 10 to the 4th, which represents 10,000. So specifically 5 times 10,000 would get us the 50,000 here. Now, if we were to represent these dots and count how many there were in base 10, and that's just counting based on our number system, what we would do is we would say, well, we need to group it into powers of 10. And some of the first few powers of 10 are 10 to the 0 is 1, 10 to the 1st is 10, 10 squared is 100, 10 cubed is 1,000, 10 to the 4th is 10,000. And the way we figure out how to express this in base 10 notation is we think, what is the largest category of base that fits into this number? Okay, so for instance, we know that there's definitely not 10,000 dots in this picture, definitely not 1,000, not even 100. Now there is more than 10, so the first thing that we're going to look at is how many sections of 10 dots can we form? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we group all of these together, we would get that there is 1 times 10 of these. 1 times 10 to the 1st, or 10 of these dots. Now that leaves 2 remaining dots that we can consider as the next lowest power of 10, 10 to the 0. So we've got 2 times 10 to the 0, and that would give us the digit 12, because we've got a group of 10 plus 2 ones, and that would be 12 in our normal base 10 system. Now, if we wanted to express these same 12 dots in a different base system, let's first start with base 2. Whenever we're thinking about expressing this as a base 2 number, so we're going to go from 12 in base 10 to, we'll figure out what digit represents that in base 2. To begin, whenever you're going from our regular digits, a base 10 digit, in our case 12, to a different base, I think it's helpful to first write out the powers of that base. So powers of 2, and we would start with 2 to the 0 would give us 1, 2 to the 1st would give us 2, 2 squared would give us 4, 2 cubed would give us 8, and if we wanted to, we could go further. 2 to the 4th would be 16, but since we've only got 12 dots, that surpasses it. So you would write down the powers of the base that you're looking up until you get to a power that would surpass the amount of items that you have. So we're only interested so far in the powers of 2 from 0 to 3. And we would ask ourselves, how many of this largest base could we separate from our group? So we would count off 8 of these. 1, 2, 3, 4, 5, 6, 7, 8. So we've got one grouping of 8 items. So we'd express that 1 times our grouping of 8 items. But since this is base 2, we express 8 as 2 cubed. This helps us focus on the fact that this is base 2. Then we've taken care of this representation, so we go to the previous base, 2 squared, and we ask ourselves, are there any groupings of 4 items, and we see that we've got 4 items here. This is one of the groupings of 4, or 1 times 2 squared. And if we add these together, that accounts for everything, but we've got to account for the fact that there is no representations for the 2 to the first, and no representations for 2 to the 0. So the way we would write that is, since there's nothing else to be accounted for, you would say plus 0 times 2 to the first plus 0 times 2 to the 0. And that takes into account the fact that you've got no other items to go towards these groupings. So as a base 2 number, whenever we're talking about turning from expanded form to a form of a certain base, we know that we've got a positional number system. So the fact that there's 0 of the ones, we would say 0, 0, 1, 1. And the digit is 1, 1, 0, 0. And then since it's base 2, you make a superscript, so smaller, in the bottom left corner of the number to indicate that this is 1100 in base 2, which would be very different than 1100 in base 10. Okay, so it's 1100 in base 2. Next, we're going to convert the same number 12 to now its base 3 format. So we always begin by off to the side writing out the powers of that base. So we'd start 3 to the 0, anything to the 0 is 1. 3 to the first power, that would be 3. 3 squared would be 9. Now 3 cubed to the next exponent of 3, notice we're increasing the exponent by 1 each time, would be 27. But since there's only 12 dots, we have kind of passed over the amount that we need to include. So we don't really need to consider this for this example. So the powers of 3 that we're going to be looking at are 3 to the 0, 1, 3 to the first 3, 3 squared, 9. So then you go to the highest power of the base that we can consider, 9, and you kind of section off any of the things that represent 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. This grouping represents one of the groups of 9. Then of the remaining items, you go to the next highest base, the previous one, and we say, can we section off any groups of 3? Okay, we've got exactly 3 of these, so we would say then we've got one of the groups of 3 that we're adding to that. Then you look, we've got to account for the last base, but we've actually got no dots left remaining, or no digits left, so we would say plus 0 of the ones. Now, whenever we go from expanded form to how we write it in base 3, you would take the digits in front of the base, remembering that it's a positional number system. So the ones place goes in the ones, then the second position would be 1, third position would be 1. So we've got 110 in base 3. And we've got to write that subscript there because it indicates that this is 110 in base 3, not 110 in our normal representation. Next, we're going to translate 12 from base 10 to some value in base 4. I recommend you pause the video at this point and work through this problem as we've done the previous 2 iterations. Your hint is to first write out the powers of 4, group them, and then write out the value in base 4 notation. Unpause when you're ready to check your work. So we always begin with 4, anything to the 0 exponent, that's 1. Then 4 to the 1 is 4. Now 4 squared is 16, and we don't need to go through any higher powers of base because at this point we've already surpassed the amount of items that we're trying to account for. We're only accounting for 12 items. So we think, how could we separate the list of items into groups of size 4? So we first count if we've got 4 here. And unlike before, when we could only count one of the largest sets, we now have multiple groups of 4. We've also got a group of 4 here and a group of 4 here. So the way we would represent that is that we've got 1, 2, 3 groups of 4. 3 times 4 to the 1. And then you always have to go to the previous bases as well. So we've done for the 1, and we see that there's no items left to account for. So we've got 0 of 4 to the 0. The way we would express this as a base 4 number is then 30 base 4. And always spell the base. That way the superscript, if we wrote 30 subscript 4, this could very quickly start looking like 304. So for that reason, we spell out the base as the subscript below the number. Okay. Our last one for this example is going to be taking 12 to base 5. I recommend you would pause the video, work through it, and then unpause to check your work. Writing out first the powers of 5. 5 to the 0 is 1, 5 to the first is 5. 5 squared is 25. Now that surpasses the amount that we're trying to account for, so we don't need to go any further than this. We group them into the highest base that we can, so 5 things. And we can actually form 2 groups of 5. Now, we can't form any more groups of 5 because there's only 2 things remaining there. So we would write we've got 2 of the groups of 5. And then we would go to the previous base, which is groups of 1. And we've got 1 of those and 2 of those. So we would say plus 2 of the groups of 1. Writing that as a base 5 number, that would be 22 base 5. So 12 is 22 as a base 5 number. Now we're going to go over some more examples, and we're going to leave the dots behind for now, but it's the exact same idea. We are writing out the powers of the base and then grouping it into different categories that fit that and writing it as a positional number. So refer back to these ideas as we go through the next examples. Now first, a bit of notation. If you see 43, since there's no subscript, this is just to be intended as 43 base 10, which is what we might think of as our normal 43. That just means 40 plus 3. Okay. But if instead you saw 43 subscript 6, then this is intended to be considered 43 base 6, or you could read this as 43 base 6. And as a number, we then have to consider it in the positional number system of base 6, not base 10. So the first digit to the right would be 6 to the 0 power to represent the ones, and we've got 3 of those, plus the next digit represents the next exponent on 6, so we increase the exponent by 1. So now we've got 6 to the 1, and we've got 4 of those. This is the same as 4 times 6 plus 3 times 1. 4 times 6 is 24, plus 3. So this would be R27 in base 10. So 43 base 6 is equal to 27 in base 10. And then remember, base 10 is our number system. Another way you might see this is instead of writing base 10, you might also hear decimal form. So that's just another notation for base 10 is decimal form. For this example, we want to convert the number 1,231 in base 4 from its base 4 value to its equivalent value in base 10. This is just our normal number system. And the way you would do this is you first write out the 1,231 base 4 in the expanded notation for base 4. I always begin with the farthest number to the right. That's going to be where you have, so it's base 4. So it's 4 to the 0. And how many of those do you have? 1. Okay, let's do some higher. Since it's in the first position, it goes there. Now next we've got in the second position a 3. So what happens is we increase the exponent by 1. So it's now 4 to the first. The reason it's 4 is because we're in base 4. And how many of those do we have? We've got 3. And then we add that 2. Okay, we go to the next position over. There's a 2 there, so we increase the base exponent by 1 again because we're moving to the left. Okay, so we got 4 squared, and how many do we have? We've got 2. And then finally, the last digit, we increase the exponent by 1, so it was 4 squared, now it's 4 cubed. How many do we have? We've got one of them. Okay. And now we'll just simplify this piece by piece. So we've got 1 times now 4 cubed in my calculator is 64. So 1 times 64 is 64, plus 2 times 16, plus 3 times 4, plus, okay, we know 4 to the 0 is just 1, so that's 1 times 1. We are going to simplify each of the multiplications first and then add them all together. So this would be 64 plus 32 plus 12 plus 1. Add all these together in our calculator and get the final value in our base 10. And we would get 109. So 1, 2, 3, 1 in base 4 is equal to 109 in base 10, or we could just write this as 109 because whenever there's no subscript of a base value written, that's implied to be base 10, our normal system. Now in this example, it's important to note that we are going from a non-standard base back to base 10, and we do so by writing out the expanded form of the number in the proper base. So we wrote out the expanded form, and then it's just gradual simplification of each term until we can add it all together to get our final answer. So that's like some base, non-standard base to base 10. This is the procedure. In our next example, we're going to see how do you go from a base 10 number to a non-standard base. So there's going to be 2 directions that this will go. We've seen the first way. Now let's see how we go from our number system to a non-standard base. In this example, we're asked to convert 497, since there's no subscript, this is implied in base 10 or our number system, to base 5 by 2 methods. So we're going to go through method 1 first. And with this, you'll never be asked to do a particular method. I would just say watch the video, work through the example, and see which method do you prefer, and then just do all the subsequent problems in that method. So just choose which one appeals to you most. Since it's base 5, in method 1 we would begin by just writing out the powers of 5, starting at the lowest, so 5 to the 0 is 1, 5 to the first is 5, 5 squared is 25, and we're going to keep listing powers of 5 until the next power of 5 would surpass the digit we're looking at, in our case 497. 5 cubed is 125. 5 to the 4th is equal to 625. And at this point, we've surpassed the 497, so we can kind of scratch that off the list, and we know that we've only got to work with these ones. Now, it's just like what we did before with the dots, except in this case, we don't want to draw 497 dots and then separate them into groups of 125, groups of 25, groups of 5, groups of 1. That is the method we're going to do it, but we're going to do it symbolically through division. So instead of actually drawing them out and separating them, we are going to think, how many times can 125 divide into 497 evenly? And then how much is left over that we would then account for the remaining bases? So both methods are going to involve some long division. So you would think, you can check with your calculator, we're going to look for even multiples, so we know like 125 times 1 is 125. Let's see if we could get closer to 497. 125 times 2 is 250. 125 times 3 would be 375. 125 times 4 would be 500. So we see we can't go all the way to 4 because that would surpass 497, but we could multiply 125 exactly in 3 times. That would get us to, so we've got 497 minus 375. We subtract those, and we would be left with 122. So the way we're going to think about this is, all the while we're going to keep track of things below. We've got 3 of the 125 groups, so we'd express it as 3 cubed plus, okay, now to account for what's remaining, we've got 122 other things that we have to account for in the remaining bases. So we've taken care of this, and now the 122 remainings will be accounted for with the lower bases. So next we ask ourselves, well, we go to the next lowest base, or highest base. 25 goes into 122 exactly how many times. If you need to off to the side, or you could do this in your calculator, 25 times 1 is 25. So this is long division. If you're comfortable with this, you can do it definitely faster than this. I'm just showing another way to work through it. 25 times 3 would be 75. 25 times 4 is 100. 25 times 5, notice I'm multiplying it by integers that are increasing, is 125. At that point, we've surpassed what we're looking at. So 25 goes into 122 exactly 4 times equally, and that would give us 100 that we subtract. That means there's 22 left over. So then we say there's 4 of the bundles of 25. So we express it as 4 times 25 is expressed as 5 squared. 4 times the 5 squared. Plus, okay, and now with this remaining amount in the remaining bases, we've got to account for 22 items. And we now have these two bases remaining. So then we ask ourselves, how many times will 5 divide evenly into 22? Well, we know 5 times 4 is 20. So when we subtract that, we've got 2 exactly left. That means we've got 4 of the bundles of 5. So we would write plus 4 times 5 to the first power. And then what's left with this is we've got to account for the remaining 2. But we've only got one base left to do that. There are, how many times could you separate the 2 dots into groups of 1? 2 ways. So we'd say plus 2 times 5 to the 0. Now, you could, as long as you use your exponents correctly in your calculator and you maybe separate these and then add them, you could check using your calculator. If you type this in correctly, you should get exactly 497. So that's a quick way you can check your work. To finish this problem, we need to take this expanded notation and rewrite it as a positional number in base 5. So that's going to be starting 3, going down to the right, 4, 4, 2. And that would be 3, 4, 4, 2, and then you've always got to write the base that it's in, base 5. Okay. So with this method, definitely have quite a bit of scratch paper ready. Work through the long division. Think of it as symbolically forming those bundles of groups of items. Now let's look through the next method. So it's doing the same thing, maybe in just a little bit more different looking format. Okay. In this next method of taking 497 and base 10 to a base 5 number, you begin by starting with the base that you're looking at, in this case base 5, and then you can draw this little angle as just an organizational tool, and you put the number that you're dividing or that you're trying to convert into this box. And then in your calculator, you are going to take the number that you're trying to change to a different base, and you are going to divide it by the base you're interested in. When I type this into my calculator, I get exactly 99.4. So what this means is it goes in 99 times perfectly with, now we need to see exactly how much is left over. The 0.4 as a decimal is not as helpful to us. So what we could do is we would take 5 times 99. We see that that's 495. So it goes in 99 times perfectly. And then we've got a remainder of 2 because we're 2 away from 497 if we're at 495. Now all of this can be done in the calculator. So what you would do next is you would write out that this goes in 99 times with a remainder, this is our remainder column, of 2. And then you would see, okay, how many times does 5 go into 99? So 99 divided by 5 is 19.8. The 19 tells us that it goes in 19 times perfectly. We've got to figure out what the remainder is. So we would say 5 times 19 would be exactly 95. And we were trying to get to 99. So we see there's a remainder of 4 left over. So we would say our remainder is 4. So we're first writing how many times it perfectly divides, and then the remainder to the side. You write the 5 again, just this kind of stair step. 5 goes into 19. Well, we could see that exactly 3 times, but 5 times 3 is 15. So what would be the remainder? Well, if you're at 15 but you want to be at 19, you would see there's a remainder of 4. Okay, that we would then try to divide by 5. 5 goes into 3 exactly 0 times, but there'd have to be a remainder of 3 left over, 3 ones to take its place. And the way you know that you're done with this method is whenever you keep doing these divisions and writing out the remainders, and you finally get to the 0 at the bottom. That's whenever no more work needs to be done. Now the way you find out how to express this as a base 5 number is, now the trick of this method is that once you finish with the remainders, you then write the remainders in reverse order. So you go from the bottom up, so it becomes 3, 4, 4, 2. We are working in base 5, so we have to indicate that with our subscript. So always remember with the remainders to, this is the number from the left, and then write it going up like that. Okay, so we see that we would get the same answer with either method, so it's just going to be your preference which you would prefer to work with, either method 1 or method 2. Now these next two examples are related. Let's read through both of them and then we'll work through them one at a time. Our first example asks us to convert 234 in base 5 from a base 5 number to its equivalent in base 10, which we would recognize as the same as decimal form, which we can think of as the same as our normal number system. Okay. Then the next question is convert 234 base 5. So we see it's the exact same number. First, in this one, we're converting it to base 10, whereas in the next example, we're going to convert it to base 3. Let's do the first one, and then we'll talk about how these problems are somewhat related. So since we've got something already written in a non-standard base and we're going to base 10, this is the reverse of the problem that we just did before. So we just need to write out this number in its positional number system, so it's base 5. I like to start with the smallest digit. We know that's going to be the same as the base, which is 5 to the 0 power. We have 4 of those, plus the next digit. We increase the base by 1, so 5 to the first as we move to the left. We've got 3 of those. As we move to the left again, we increase the base one more time, plus 5 squared. We've got 2 of those. And then what we're going to do is we're just going to simplify these 3 terms and then add them together. So 5 squared, we could rewrite this as 2 times 25. 5 to the first is just 5. 5 to the 0 is 1. So we could rewrite these as this, a little bit more simplification. 2 times 25 is 50. 3 times 5 is 15. 4 times 1 is 4. And definitely you can do all of this in your calculator as well. Adding these together, we would get 69. And you can leave it as just 69. Remember, when we're in base 10, it's implied that it's base 10 if there's nothing written. And you could also write it as 69 base 10 if you like. But either of these would be fine. Now in our next example, convert 234 from base 5 to base 3. Whenever you're going from one non-standard base to another non-standard base, it's helpful to first go from the first group to a base 10 number, and then from a base 10 number to the final base that you're looking at. Now, normally you would actually have to complete this step separately, but since we've already converted 234 base 5 to its base 10 value, we know 234 base 5 is equal to 69 in base 10 from our previous work. So normally you would have to complete this step as part of this problem, but we are going to base our work from the earlier example. And now we are here, so we need to go from 69 in base 10 to this as a base 3 number. To do this, since we're looking at base 3, I recommend you write out the powers of 3. So going from our number to a non-standard base, write out the powers of the base you're looking at. 3 to the 0 is 1. Remember, we're going to keep increasing the exponent on the base until we surpass the number that we're looking at, in our case 69. 3 to the 4th equals 81. Now 81 is higher than the 69 that we're looking at, so we know we're only considering these different powers of 3. Just to show both, if you know that you prefer method 2, you might skip ahead already, and if you're comfortable, I would pause and then unpause to check your work. So for method 1, the way you do this is you think exactly how many times could I bundle 27 from the 69. So 27 times 1 is 27. 27 times 2 is, and we could, if you do this on your calculator, it will save you time. I'm just drawing it here so you can see. So you keep multiplying 27 by increasing powers or integers until you get past the number you're looking at. So it would go exactly 2 times into 27. So we'd have 2 times 27, which is expressed as 3 cubed. And then we get to 54. Now we were at 69 and we got to 54. Let's see how much is remaining to account for by subtracting. So the 2 times 3 cubed accounts for 54 of the 69 items, but there's still 15 remaining here. So we go to the next highest base and we would see, well, 9, we could bundle 9 items of the 15 exactly 1 time. 1 times 3 squared. But that would leave, if you've got 15 items and you're bundling 9 of them, you have 6 remaining. So the remaining 6 would have to come from the remaining 2 bases. Okay. So for this 6, we next are looking at groups of 3. We know we could form exactly 2 groups of 3 to account for 6 perfectly, and that would leave us with 0. So there's 0 things to account for, but you do have to go through all of the bases. So our last base to account for is 3 to the 0, and since we have everything accounted for, we want 0 of that. And then remember, the final step of this method is just to write it as a positional number. So this would be 2120, remembering that it's now in base 3. Okay. So that's method 1 of going from a base 10 to a non-normal base. If you prefer the method 2, the way we would begin that, okay, we would first say in our calculator 69 divided by 3, and that would give us exactly 23. Now in this case, it's exactly 23. There's no decimal, so we know the remainder is 0. Now you keep going, remember, until after you do the division, what you write next here would be 0, not when you get a 0 remainder. So we keep going. 3 divides into 23. 7.6 repeating. So we know it divides perfectly 7 times. And let's see exactly what the remainder would be. 3 times 7 is 21. So we have 21. We want to get to 23. So the remainder would be 2. Now we see how does 3 divide into 7. 3 divides into 7 2 times equally. 3 times 2 would give us 6. We've got a remainder of 1. So then 3, so divides 2 times. Now 3 goes into 2 0 times, but the remainder would be 2. And then remember, the trick from this system is then you've got to take the values that you found, and this is the starting point, and then it decreases that way as you go up. So we've got 2, 1, 2, 0 in base 3. So whichever method you prefer, remember you would first take 2, 3, 4 base 5, turn it into a base 10 number as we did in this example, and we got 69 base 10. Then you would take this base 10 number to a base 3 number using either method 1 or method 2. We do get to the same answer in either case. Now in this example, we've got convert 654 to base 7. Whenever there's no subscript, remember that's an implied base 10. So in this case, you could choose either method 1 or method 2 to work through this answer. I'm going to recommend that you pause the video and, based on whether you prefer method 1 or method 2, work out your problem. Unpause and you'll see the solution for both on the screen, and then just check the work for whichever method you prefer. So either through method 1 or method 2, you would get the same answer. Now, one of the most common base systems, and the one that we might have seen the most just in our everyday life, is the binary number system, which works with the way computers communicate. So that would be binary is known as base 2 system. So if we're converting 110101 in base 2 to a decimal form, we need to see this as expanded notation. So we first need to write this out as expanded notation in base 2. I like to start at the farthest right. That is 1 times the first base 2, 2 to the 0, plus, next we would have the next base, so we increase the exponent by 1. 2 to the first, we're multiplying that by 0. And then we keep increasing the exponent by 1 as we move to the left, plus 2 squared. How many of those do we have? 1. Plus the next, we increase the exponent by 1, and we've got 0 of those. Plus 1, we increase the exponent again to 2 to the 4th, we've got 1 of those. Plus our last digit, we increase the exponent by 1, and we've got 1 of those. And now we just need to simplify each of these separate terms piece by piece, and then we'll add the total together. 2 to the 5th is 32, so that's 1 times 32. 2 to the 4th is 16, that we're multiplying by 1. So we simplify each of these. 1 times 32 is 32, plus 16. 0 times anything is 0. 1 times 1 is 1. Adding all these together, we would get 53 is the base 10 form of 110101 in base 2, or in binary. So just a few definitions to know. If you're ever asked to convert to binary, that's base 2. If you're ever asked to convert to decimal form, that's base 10. So I recommend you do the homework assigned and reach out to me through Canvas if you have questions. Then within the deadline, complete the quiz from this section. So if you have any questions, do feel free to message me on Canvas. Thank you.